Welcome everybody to America's favorite geometry game show. Is it a parallelogram? Our goal in today's lesson is to show that we have parallelograms and what stipulations are there to show that something is definitely a parallelogram. The first thing we should turn to is the definition. The definition says if it has four sides, it's a parallelogram if and only if both pairs of opposite sides are parallel. So some of these quadrilaterals look like parallelograms, some of them don't, but the thing we need to check is to see if both pairs of opposite sides are parallel. And so if I see parallel and parallel, then I can say yes, that's definitely a parallelogram. So here again, opposite sides being parallel, yes, that one's a parallelogram. The bottom one looks like a rectangle, but rectangles have both pairs of opposite sides parallel, so I guess that means rectangles are parallelograms too. The only one that I don't think we can say is a parallelogram is this one. It only has one pair of opposite sides that are parallel. So I'm going to say no, that is not a parallelogram. Yesterday we learned 5 properties that if you knew it was already a parallelogram, if somebody said, hey, this is a parallelogram, then you can say both pairs of opposite sides are congruent, or the consecutive angles have to be supplementary. But that's when the given information is that you know you have a parallelogram. Today's lesson, we are trying to prove that we have a parallelogram. Remember, we're deciding if there's enough information to show that's a parallelogram. And so far, we just have that one criteria that tells us if something's a parallelogram, and that one is that both pairs of opposite sides are parallel. And that comes from the definition of a parallelogram. And because definitions are if and only if, it works saying if parallelogram, then both pairs of opposite sides are parallel. But it also works to say if both pairs of opposite sides are parallel, then it's a parallelogram. Remember those biconditionals, they go both ways. And so that's our first thing that we can use to check to see if we have a parallelogram. So here I have the 4 lengths given in this diagram. And as long as I can adjust those so that the opposite sides are congruent, once the opposite sides are congruent, then it's a convincing parallelogram. This new theorem, Theorem 8.7, tells us that if both pairs of opposite sides are congruent, then you're guaranteed to have a parallelogram. So we're going to add that as our second way to tell if you have a parallelogram. If you can guarantee that both pairs of opposite sides are congruent, then you have a parallelogram. And this one definitely doesn't look like a parallelogram in the beginning, but as I adjust those angles, if I can adjust them so that the opposite angles are congruent, then it starts to look just like a parallelogram. And Theorem 8.8 says if both pairs of opposite angles are congruent, then it's guaranteed that that quadrilateral is a parallelogram. So we'll add that as our third way to check to see if something is a parallelogram. If you can guarantee that those opposite angles, both pairs, are congruent, then you know you have a parallelogram. Let's play the game show now. Are any of these definitely parallelograms? I see this one down here with the opposite angles. Do you see that? I have both pairs of opposite angles are congruent. And that is definitely one of the ways I can say that yes, that's definitely a parallelogram. And I guess this one would work too. Both pairs of opposite sides are congruent. They all happen to be 12, but the opposite sides match. And that's one of the ways that we can tell that we definitely have a parallelogram. Now these top two definitely look like parallelograms. I've got an 85 and an 85. I've got one set of opposite angles congruent. Is that enough? This looks like a convincing parallelogram. I've got an 85 and an 85, and honestly these look the same too. But see what happens when I drag these around. Just because those two angles are 85 degrees does not mean that that's a parallelogram, right? We can sort of make any shape we want. And just because those are 85s doesn't mean it's a parallelogram. And this next one certainly looks like a parallelogram. I have one pair of opposite sides that's congruent. Looks like a parallelogram. Is it definitely a parallelogram? And here's that example with the 30 length and the 14 and the 14. And as long as it's drawn so that that looks like it's a length of 30, it definitely looks like a parallelogram. But see what happens when I can change these up. That side length is staying 14 units long. So I still have the 14, 14, 30, but if that top length isn't determined, then it really doesn't have to look like a parallelogram at all, right? Let's see if we can find those last two properties. I built this quadrilateral so that that top length and this bottom length were constructed to be parallel. So as I move these, I'm not even allowed to move them not parallel to each other. But we know that one pair of parallels doesn't make a parallelogram. It really makes a trapezoid. But what if we made a stipulation on the length as well? What if I brought this length down to match the length of the top? That looks like a parallelogram. But I know that one pair of parallels doesn't make a parallelogram, and one pair of opposite sides, congruent, doesn't make a parallelogram. But what if we had parallel and congruent? So theorem 8.9 is kind of the new one. It says if you have just one pair of opposite sides that are congruent and parallel, then the quadrilateral is a parallelogram for sure. So we're going to make that our fourth one. One pair, just one pair of opposite sides parallel and congruent. So I'd be looking for parallel on one set of sides, but also those sides are congruent to each other. I wonder if we can make this a parallelogram just based on those diagonal lengths. I know that a property of parallelograms is that the diagonals bisect each other. So do you think if I adjusted this to make it so those diagonals are bisecting each other, then it's guaranteed to be a parallelogram? I feel like that looks pretty convincing. I have those diagonals bisecting each other, and it wound up looking like a parallelogram. And the last one, if you can get those diagonals so that they bisect each other, then you know you have a parallelogram. The diagonals bisecting each other makes it a parallelogram. Let's draw in those diagonals. And if we have that midpoint in the middle, tick, tick, double tick, double tick, if we're sure they're intersecting at their midpoints, then we know it must be a parallelogram. How could we prove for sure that this is a parallelogram? I see that I only have one pair of opposite sides that are congruent, and I've got these angles that are congruent, but they aren't even both interior angles, so what's that all about? But you know what kind of angles they are? Aren't they corresponding angles? They're both sort of in the same upper right-hand corner. And if corresponding angles are congruent, then that tells me that those two lines must be parallel. So really, those two angles are telling me that this side and this side are parallel. And look at that. That's our one where we have just one set of opposite sides, but they're parallel and they're congruent. So we just kind of talked our way through how we would prove that. We aren't actually going to write a proof, but just explaining how you would come to that conclusion is good enough. On this bottom one, I'm actually going to show that this is definitely a parallelogram. It looks like one. And I can show this in lots of different ways. I could find some slopes. Do you remember why slopes are going to help me talk about parallelograms? Slopes tell me if I can say that sides are parallel, right? If we have the same slope, then we have parallel lines. I could also use the distance formula. If my distance formulas match on two segments, then I would know that I have congruent sides. So I'd say those are our two best tools. We could check slopes or distances or maybe even both. If these lines weren't so slanty, I'd probably just count the boxes to find those lengths, but the distance formula can get a little long and tedious. But slope is actually pretty easy to calculate, right? Rise over run. So if I'm going from A to B, I would go down 2 over 3. So the slope from A to B is down 2 over 3. And I could easily do that on each of those 4 segments. BC, I guess I could go this way, up 7 over 1. For CD, I always like to start at that left point. I could go down 2 and right 3. And that fourth side, I could go up 7 over 1. Up 7, right 1. Remember that even if you did that in reverse order, if you went left 1 and down 7, the down 7 and the left 1 would still give us a negative over a negative makes a positive. That would still give us a positive slope of 7 over 1. So if you were to calculate those 4 slopes, that would tell me that I know that AB is parallel to CD. And it would also tell me that BC is parallel to AD. And that's enough to prove that that's a parallelogram, because remember the definition says if and only if both pairs of opposite sides are parallel. Remember, I could also have used the distance formula to find the lengths of those 4 sides, because I know that if the opposite sides had been congruent, if those lengths had matched, that would have been another way that I could show that that's a parallelogram. And thanks for playing, everyone. Is this a parallelogram?